Today, we have Professor Igor Pak from UCLA, who works in combinatorics and discrete probability broadly defined. So Igor was born in Moscow, Soviet Union, which is a nice place for a mathematician to be born because it's an empty set now. So who can boast he was born in the empty set? He did his undergraduate studies at Moscow State, and then he did his PhD under Percy Diaconis at Harvard on random walks and groups. And later on, he did a postdoc in Yale with Laszlo Lowish and a few other research stays at different places, including the Mathematical Sciences Research Institute and the Hebrew University of Jerusalem. So now he is a professor at UCLA. He was an invited speaker at the International Congress of Mathematicians in Rio in 2018. So today, Igor will speak about combinatorial inequalities. So, Igor, we are very happy to have you speak here at the Vinberg Distinguished Lecture.
Thank you so much for the introduction, and it's a pleasure to give this lecture. I just want to, before I begin, I just want to tell all the people in the audience, I can see you if you choose to make yourself visible. So I encourage you to do so, because that's actually helpful to everyone to see faces and all. So if that's not against your some kind of beliefs, please make yourself visible. All right. As I said, it's a pleasure to be here, and I'm really happy to give this lecture. I remember Ernest Borisovich rather fondly when he was teaching when I was at Moscow University, and obviously before and after I left, I don't think my lectures can be compared to his lectures, but I'll try anyway. So let's begin. The way I like to do this is I'm going to be occasionally asking you if you're understanding everything, can move on. So when you want to say yes, do emoji something, or even better, do this or that. Okay. So everyone ready for me to start the lecture? Excellent. Good. So we'll do. Okay. So the plan is very simple, and it's exactly the kind of plans that organizers told me to have. First, to give an overview, and then I'm going to talk about some recent work I've done. So there is not much of a plan, and we'll make some kind of break. I'm sure organizers will remind me at what point I need to make a break. And one thing to remember is the following slogan. I'm going to be talking about combinatorial inequalities, and some of them are better than others. But just like combinatorial inequalities, some are better than others. There are proofs, some proofs are better than other proofs. And you need to remember that good inequalities really deserve to have a good proof. If they don't have a good proof, that means that we don't really understand what this inequality is doing. And we need to do that. So now the talk officially begins, and I'll start. So I'm going to start with a long overview of various rather simple inequalities, and I'm going to start with the simplest one about Fibonacci numbers less than 2 to the n. You can prove it by induction, but it's even easier if you think about it. It just follows straight from definition, because Fibonacci numbers count 0, 1 sequences of length n with no 2 1s in a row. And as such, the number of them is less than the total number of 0-1 sequences. Okay, everyone good? Remember, you need to do this. Okay. And so what is going to be? So the next inequality is a little more complicated, but just a little. So I'm saying that binomial coefficients are unimodal. So we have this inequality from left to right, and choose 0, and choose 1, and choose 2. And the proof is, again, completely trivial from a modern point of view. You just do calculations. There is an explicit formula for binomial coefficients. You divide one by the other, and you figure it out. So that is still very easy. The next one is slightly less easy, but also rather easy. So I'm saying that Catalan numbers are smaller than Bell numbers. And you can just see it from these two sequences. The first one is Catalan numbers, 1, 2, 5, 14, 42. And the second one is Bell numbers. They sort of start the same. 1, 2, 5, 15. 14 and 15 seem very close, and 42 and 52 are not so bad. But then the difference starts to emerge, and in fact, these two sequences have drastically different asymptotics. Essentially, Catalan numbers grow exponentially, Bell numbers grow factorially. They just have asymptotically, they have nothing in common. But you can prove, and there are a million ways to do this. You can prove it by induction, for example, or using asymptotics actually, and some exact formulas. Everyone good? Okay. Okay. So the next inequality you might find a little trivial, but let's go through that. So I'm saying that number of partitions actually is increasing. So P of n is the number of partitions of n. So for example, this 3 can be written as 2 plus 1 or 1 plus 1 plus 1. And I'm saying that the reason why it's increasing is because you can have a combinatorial interpretation for the difference. The difference in P of n, Pn plus 1 minus P of n is the number of partitions of n plus 1. So it's part of what's counted in Pn plus 1 with no parts of size 1. Okay, that's it's an easy exercise to see why that is true. And but that is actually from the point of view of proofs, that's a new way of proving inequality. We're saying that there is an injection from partitions of n into partitions of n plus 1. Okay, and that is which establishes this inequality P of n less or equal than Pn plus 1. Everyone good? Okay.
Yeah, I'm sorry.
Yeah, go ahead.
You gave a similar injection proof for the Fibonacci inequality. Do you have an analog? Do you have injection proofs for 2 and 3?
Yeah, I do. And but before I get yeah, I do. The answer is yes. Before I mention a little more about that, let me mention another inequality, which is somewhat similar in flavor, but a little bit different. So here it is. It's we're saying that the sequence of partitions is log-concave, which means that the log of the sequence is a convex function, concave function. And that's not actually true somewhere in the beginning, but starting with n greater than 25, it is true. And you can sort of intuitively see why that would be true. That just because the asymptotic for the number of partitions roughly e to the square root of n. So when you take a log, it becomes just the square root of n. However, saying that something is true asymptotically, that doesn't imply anything about local fluctuation. You can have lots of weird stuff happening over there. And the reason the inequality is true comes from rather much more delicate asymptotic estimates that one can do in this case. And it's still a relatively simple result, but not in the same league as the previous one. It's substantially harder. So to answer your question, it is true that inequalities 1 to 4 can be proved by direct injection. However, one shouldn't expect the inequality 5 to be proved by direct injection. The fact that you have this n greater than 25 should be a warning. There is no way this n greater than 25 could naturally come from some nice combinatorial construction. So did I write that? Yeah. So in fact, I even wrote that. In fact, the difference in the binomial coefficients is a famous sequence. It's a ballot problem due to Bertrand, which counts the number of ways and people can vote, so that k vote from one candidate and minus k vote for the other candidate, and the other candidate keeps always winning. Okay, this is a little bit similar to Catalan numbers, and that problem is a fundamental problem in kind of combinatorial probability. And in fact, I didn't write that for this inequality, there is also an injective proof, and that particular paper is what I did in my undergraduate days. This was my RU, which I did when I was an undergraduate at Moscow University, that Sasha helpfully mentioned at the beginning of the talk when he introduced me. So this is not a particularly deep injection, but I think lots of people tried to get an injection here, and that doesn't make much sense to me. So a lot of talk is going to be about injection. Can I move on? Okay. Let me see. Yeah. So here is another example. This is an example of unimodal. This is one of the most classical results in combinatorics, quite a bit non-trivial. I'm going to define Gaussian coefficient by the following formulas you see. So these are Gaussian coefficients, and that's a ratio of Q analogs of a plus b factorial, a factorial, and b factorial. And if you don't like formulas, one way to understand it is that this is a polynomial where coefficients PAB are given by the number of partitions of n. So n is the number of these plus squares, and a and b are the sizes of the box. So that's the number. So PAB of n is the number of partitions which fit into a rectangle. And now, just like with binomial coefficients, for the coefficients of Gaussian polynomials, we have the unimodality property. That's why I go until the middle. After that, they're going to fall symmetrically back. Okay. Let me give you an example so you can see. So here is an example, and you can see that it starts 1, 1, 2, 3, and so forth. So the whole thing is unimodal. Okay. Now, that is everyone clear about the result? That doesn't sound fancy, except that was an open problem for about what is it, 23 years. So this was essentially conjectured by Kelly, and I'm not 100% sure of history, but I think Kelly just said the following is going to be true. That just flat out. You know, we can all see that it's going to be unimodal, and it took a while until Sylvester wrote a long article explaining why that's true from invariant theory point of view. He actually had to invent a whole bunch of tools for that, and he also had a flowery introduction saying it took humanity almost quarter of a century, and there was some religious reasoning that he gave why these things were epistemological stuff. But then the theorem became so famous, it was reproved a large number of times. So famously, Stanley used the Hart-Lefschetz theorem to prove that, and Proctor realized that one can convert Sylvester's proof into claim in representation theory of SL2s, which can in turn be converted into just a basic result in linear algebra, which is how he presented the proof. Casey O'Hara in her dissertation gave a combinatorial proof, but not injective proof. essentially her proof used a lot of formulas. And more recently, with Greta Panova, we gave another combinatorial proof using technology of Kronecker coefficients, which proves more than just Sylvester's theorem, but it's not a particularly easy proof at all. None of that is something that I can explain in 2 minutes. And so you would say that this is a difficult problem, and there is no injective proof known. So one way to phrase it is there's no obvious combinatorial interpretation or natural combinatorial interpretation for the difference p n minus n minus 1 is known. And you would think it would be easy. You can just add one square somewhere, right? Just find some corner, add a square so you can remove it. That doesn't work. And that's where we are. Everyone with me? Yeah, we can move on. Any questions so far? I should have asked earlier. Okay. Well, if there are no questions, let's go to the next item on my list. And the next item is that's a log concavity of k-matching numbers. So what I mean by k-matching is collection of k edges. So there are k edges here. There you can sort of see them in red, which are disjoint in the graph. So let's start again. We have a graph G with a set of vertices E, set of edges E, and we're looking at k subsets of edges which are disjoint. The number of such subsets is going to be mk of G, and turns out that it's actually we have a log concavity property of that. So it's a little similar to log concavity of partition numbers, and but that's and it's a stronger property than unimodality that you've seen before, but that is actually a little harder to prove. And so this is a famous result by Hellman and Lieb, and you can even see how famous it is from 752 citations. That's not something that we typically get in our math papers. I mean, in fairness, this is a famous result also in statistical mechanics, so it's not traditionally combinatorial, but I consider that result to be a combinatorial result, and the proof is what we would call now algebraic graph theory. So they're looking at eigenvalues, interlacing of eigenvalues, and that result, it was a foundational result in a whole host of results, including recent work by on Ramanujan graphs and so forth. Let me not say too much about that. But as such, you would think that this proof would have an injective proof. This inequality would have an injective proof, and it does. So this is what I wanted to show you. This is maybe the first explicit proof. I'm not completely sure. I'll just hint how that works. And is everyone clear about what the inequality says?
Sorry, can I just ask, you're saying this K matching number is related to a spectral gap somehow?
Oh, yeah.
Is it easy to see that?
Yeah, more or less. So it's a so the genetic function is basically characteristic polynomial.
Oh, okay, then it's directly.
This is not. I didn't write that, and but yeah, it's directly related to eigenvalues. But you have to be a little more careful, and I'm not prepared to be more careful in this particular instance. So let me see, where am I? Oh yeah. So here is so what I wanted to do is sort of set up a framework. How would such a combinatorial proof even work? And the way to do it is to pick one item from here, one item from there, and then merge them together somehow, and obtain. So those are two items, and obtain two items from from pair of k matches. Do you see what I mean? That's how you would want the injection to work. And so in this particular case, that's actually easy. So, or in the case of this inequality, it's actually easy. So in this example, I have k equal to 3, and so I have one matching that has 4 edges; those are red, and another matching which has 2 edges; those are blue. You see what I mean? And just for the record, I'm giving a proof by Christian Krathaler. So what I do is I overlay one on top of another. And when I do that, what happens is I create some kind of cycles and paths. In this particular case, I just have 2 paths that are created. And now what you can do is you can take paths. Paths come in different type. There are those which go red, blue, and there are those which go blue, red. So they have even number of edges, odd number of edges, and so forth. And what I do is I would have to find a way to recolor one of the paths to undo the disbalance. Okay. And then I would have the same number of red and blue edges. How do I do that? That's it's a little more complicated, but not too complicated. Essentially, I'm going to have a bunch of balanced paths with or cycles which have equal number of red and blue. I do nothing to that. I'm going to have some where there is there are more blues than red, and there are some where there are more reds than blue. Okay, and now it boils down to unimodality of binomial coefficients. I need to embed those with this kind of disbalance to those within that kind of disbalance. Since I never actually told you how to do injective proof for binomial coefficients, I'm not gonna do that now, except to say that from this point on, you use a Bellet problem. But that's roughly how you do it. So in that particular case, what you do is you recolor all those edges in the red-blue path that you see over there. I don't know, that's an ugly way to trace the path. You recolor all those edges, and instead of that red, you get blue, blue, red, blue, and so forth. Let me switch back to so you recolor you recolor edges along one of the paths, and then you get a little more blues than what you used to have, and a little few reds than you used to have, and that's how you get a balanced number of K matching on each side. Okay, again, one should do this carefully, and but that's from what I already told you, you can figure it out, and if not, you can open just a couple of paragraphs and Krathaler. It's a very short paper how to do that. Can I move on? I'd rather
actually ask a very quick question.
One of you.
Oh, go ahead, Jordan. Sorry.
In this case, do you have an interpretation for the difference? Like, can you count the balanced ones that sort of don't arise from this construction?
You totally get interpretation. That's because the injective is completely explicit and can be done in polynomial time. So you can decide whether the image of the injection is in the image, whether a pair of matchings is in the image or not. And therefore, in the combinatorial interpretation, sorry, I think I see only your eyes, Jordan. So you can so you can decide whether if you can decide whether it's in the image, then you can just say the difference is the set of pairs of matchings which are not in the image of anything. That's my combinatorial interpretation for the difference.
Can I just ask a really stupid question? Somehow in the binomial coefficients, it seems like a linear. When you take this difference, it's a linear difference, whereas here it's the log concavity. So where should we see the square of the matching number being related to
So the reason is you're looking at the difference on kind of like superstructure, which think of path as being exponentiation. So now we're doing in the binomial coefficients here you use new modality on paths of different colorings rather than on k-matching themselves. So when you have an extra structure, that corresponds to exponentiation. It's a very good philosophical question, not really something that formalizable, but yeah. So now I wanna talk about so I'm gonna sort of progress in direction of hardness at least until now. So now I wanna consider similar question. Consider the following forest numbers. And by that I'm gonna talk about fk of g as the number of spanning forests. So you can see a forest in red on the right hand side. I don't actually know how colors are projected. So spanning forest means it contains all vertices. So I take a subset. So essentially, I take a subset of edges of my graph and ensure that there are no cycles. Those are forests. Subsets of k edges with no cycles are spanning k forests. And now we have a log concavity for the number of them. Okay.
Igor, may I ask you a stupid question?
Go ahead.
What about the number of spanning trees?
That's just a number. I'm talking about this is number of spanning trees that.
Oh, I see. Because yeah.
Fn minus 1 of g.
Because it has to be the same graph, right?
Spanning trees of g. Okay. So good point. That number generalizes the number of spanning trees in the graph. And however, in this case, we don't have anything even remotely close to a nice injective proof. So in fact, until very recently, this was an open problem which was open for 45 years or so. Even though it sounds extremely simple, there was no tool to do that kind of thing. And there was a breakthrough paper by the Prasita Hukats, which resolved that problem among other problems. I'm going to mention much more about that later. This is sort of we're still in the survey stage of the talk. And the way they did it is by an amazing breakthrough by using a rather let's call it difficult algebra. So if Hodge theory, think of that as a word for a difficult algebra, and the paper is long, the paper is fancy, hard to understand what's going on, but that's what they did. Okay, so it boils down to a relatively simple result about log concavity in the number of forests. And once you have such a result, and once you have such a difficult proof, it basically begs for a simpler proof, and this much simpler proof was found later. In fact, there are two groups of authors, Brandon Hu on one hand, and group of four authors, Anari being the lexicographically smallest, and they at some point agreed to post their two papers on the same day on the archive, so that neither of them gets a priority. And that's a modern way of announcing results, I suppose. And they used a relatively similar technology of Lorentz and polynomials. I'm going to say a little more about that later. And in the second part of the talk, I'm going to say basically that I did not find a proof. I tried. I made my best effort. I did not find a proof injective proof of this inequality. However, we do have a paper where we prove this inequality by linear algebra, which is completely understandable to everyone. And Lorentz and polynomial is not super hard, but our proof is quite different and gives more. Okay, everyone clear what's going on? So the point is, even though those results are similar, forest numbers are similar to matching numbers, in this particular case, we have no idea whether this difference has a combinatorial interpretation or not. Or more precisely, from computer science point of view, one can ask, what is a combinatorial interpretation? And what I want is to interpret those numbers as a number of combinatorial objects. And the combinatorial objects should be testable in polynomial time. That's a very formal way of phrasing. And in this particular instance, we don't know if that's possible at all or not. So forget a nice injective proof. Just give me a combinatorial interpretation for the difference. The difference is non-negative. It's a non-negative integer. You would think that it should have a combinatorial interpretation, and well, not all non-negative integers have a combinatorial interpretation. So that's where we are. Everyone clear where we are? Yeah, can I move on? I'm getting close to the end of the talk, and one minor comment I want to make is that computing those numbers, in contrast with spanning trees that Sasha mentioned, you can compute a number of spanning trees in polynomial time, but computing k-forests, that should be complete. Okay, so one should not expect a nice way of computing this number rho k of g. That's not going to work. And while I am on topic of computing, let me say a little about number of spanning trees in a simple graph. So here is a very simple looking inequality, and in fact the proof is just a one-page article by Geoff Grimmett back in 1976, which I strongly recommend. It's a beautiful linear algebra exercise. Also, you can teach it to even to advanced undergraduate students in an honor class. Number of spanning. So what this is saying is that number of spanning trees is bound you can bound it in terms of number of vertices and number of edges in the graph, and here is some formula. Okay. Now, once you have a formula like that, you can turn it you can turn it into an equality of the kind we had before, and you can say, look, therefore there's got to be interpretation for some number tau, which you obtain by multiplying both sides by the denominator and subtracting. And that's where the difference between combinatorics and computer science comes in. So from computer science, there is no issue. This number, tau of g, can be computed in polynomial time. That's because we have a formula for it. Using matrix T theorem. It's just a determinant. You can compute it all in polynomial time. If you can compute it into polynomial time, therefore, it does have a combinatorial interpretation as a number of 0-1 sequences less than that number. I know it sounds silly, and that's not giving agreements, that's not implying agreements inequality. So what this is saying is, assuming you have agreements inequality, then it follows immediately then tau of g is in sharp p, just because it's an FP. You see what I mean? So I see some puzzling faces over there. Are there any questions about this?
So Igor, for me, if I had a combinatorial interpretation, I think I would mean something functorial, that if I had like an automorphism of the graph, I should get not just like a number, but a set with that automorphism, right? So like counting spanning trees, for instance, like to me, it shouldn't be called a combinatorial interpretation just because I can compute the number in polynomial time. I should have like a set that I can act on by any automorphism of the graph.
That would be you. Computer scientists would be different people.
Okay.
So the problem with your definition is that it's not a definition. What they have is an actual definition. And so showing that something is not possible in their definition is much harder. Except in your definition, it's even harder because you don't know what you're talking about. I'm not insulting you. I'm just trying, I'm generalizing the approach. And that's my typical issue with a lot of combinatorials. They want more from a combinatorial interpretation. They just don't know what they want. You see what I mean? And I have one more example before the break, and I'll let me say that example, which leads to this difference, but I'm not going to talk about computer science at all after I finish this bit. So here is a really nice. I'd rather not state Kleitman's inequality in full generality. Let me just say the following consequence or special case of that. Let H be a random subgraph of G. And by random subgraph, I mean a random subset of edges. You flip a coin on each edge. You can even fix probabilities of each edges if you want. And then I'm saying that probability that it's Hamiltonian is greater than probability that the subgraph is Hamiltonian, conditioned we know it's planar. You see what I mean? So now that might seem extremely surprising that one can actually prove that, because planarity is hard, Hamiltonicity is even harder. How on earth one would even come up with that thing? Why would that be true? And the reason is that planarity is a property which is closed down. And by that, what I mean by that is if you have a planar graph, you remove edges, it's still planar. Hamiltonicity is a property that closed up. So if you have a Hamiltonian graph, you keep adding edges. If it had a Hamiltonian cycle is still there. So there is a negative correlation between those two properties. Hamiltonian graphs like to be large, planar graphs like to be small. So if you assume that the graph is small, getting Hamiltonicity is harder. That's what this inequality is saying. Okay? Everyone clear about the inequality? I mean, this special case. Now the proof is a beautiful proof, one page by induction, and this inequality led to a large number of generalization in a rather rapid succession. The most famous one is FKG inequality, which itself is a corollary of Alexandrov inequality, sometimes called for functions inequality, and all of them have essentially the same proof. You generalize it so far that induction becomes easier rather than hard. This is sort of a typical thing that happens in combinatorics. Sometimes advanced generalization can help. Okay, I'm gonna flip the page so that you can see what we actually can do now. What we can do is we can show that some inequalities, very few, but some, are actually not on sharp P. And by that, I mean, there is no combinatorial interpretation for the difference. It took me essentially all the COVID to do this research and write this paper. That's joined with Christian Ickenmeyer, and this is 82 pages. It has lots of other inequalities and lots of other stuff. But basically, we set up a technology to prove this kind of thing, to show that not all combinatorial inequalities can have a combinatorial interpretation. And are there any questions about this claim? So this for functions is a gigantic generalization of this Hamiltonicity planarity inequality. And now in the second half of the talk, I'm gonna talk about something more specialized. So here is my mid-talk summary in case you are tired of listening to me, is that there are lots of different combinatorial inequalities. They can be easy, they can be hard, and they can be very hard. They can also be yet, open questions, I suppose. But the right approach to the inequality is by the proof. You need good proofs, and combinatorial proofs, the ones that use injection, are absolutely the best. They give you lots of implications, in particular quality condition, vanishing condition, and so forth. And often enough, you cannot have them. But also, when you don't have them, linear algebra is what is the clue to the whole thing. And that's what I'm going to talk about later. So just like with Gaussian coefficients, and and spanning forest, linear algebra is the way to truly understand the combinatorial inequalities, as far as I can tell. And so preview for the second part. In the second part, we consider only log-concave poset inequality. So I'm going to talk about posets and log-concavity. Log-concavity you've seen before. Okay, that's it. That's it for the first part. Questions about any of that?
So let's first thank the speaker.
Thank you. Thank you.
And of course, if there are any questions, please ask. I think we are going to make a little break, right? So how long will it be? Is it going to be 10 minutes, 15 minutes?
Well, I think until 20.
Yeah, 6
20.
minutes.
6 minutes.
Minutes. Okay. I don't know.
Fine.
In the meantime, can I ask a philosophical question? I mean, combinatorial inequalities, you're judging hard, very hard, easy, but sometimes they look very hard because the proof was very difficult, and then comes along a linear algebra proof, like you said, that makes something that seemed very hard into something easy just by maybe an even more clever proof.
Yeah, so this is not meant to be formal.
No, of course.
I agree with that. Things shift around. Just like, you see somebody who you think is a very clever person, suddenly they do something stupid and you reassess. Let me know.
Wait, were you referring to my definition of a combinatorial?
No, it's not nothing personal in any way at all.
But so my question was going to be, so showing that something's not in sharp P, is that a way of guaranteeing that if you prove some inequality, then it must be not easy?
Yeah. So it doesn't mean that the proof is mathematically hard, but it's saying that you should not expect a nice injective proof of the kind you've seen for matching numbers or for binomial coefficients and so forth. It's something that's that's like a stamp of approval from a combinatorial point of view. Since this is a break and we're talking philosophically, I'm personally motivated by questions. This is a Kronecker coefficient. Can we give a combinatorial interpretation for the Kronecker coefficient? What does that even mean? So asking whether it's in sharp P is a way to say that. So people have been looking for that since 1938 for combinatorial interpretation of this Kronecker coefficients. And the way to understand that is you take a product of characters and that becomes the sum of G lambda mu new character new. So just the usual product. And you would think that when you have and those are characters of the symmetric group Sn, you would think that when you have such a simple definition of non-negative integers, they would have a combinatorial interpretation. What can be more classical than characters of the symmetric group? And what I'm trying to say is that no, those are difficult. So in fact, the fact that in the inequalities that Kronecker coefficients are greater or equal to 0, that's something that we take for granted because we think it's easy, because it follows from, I don't know, Machka theorem. That's actually a deep inequality. It's not combinatorial at all. But I don't have a theorem that's saying that Kronecker are not in sharp P. Really, this is the first type of theorem that we even have. And that took me, 10 years of thinking and 2 years of working.
So do you conjecture that Kronecker is not in sharp P, or?
Oh yeah, I totally. And but lots of people conjecture and believe like a religion that they do have a combinatorial interpretation. They published lots of papers on special cases and so forth. It's a very active area of research. I just think they're all wrong. But I'm just one man against the machine. So I'll just continue The whole second half is motivated by the work I did with my postdocs with Chung, and what we did a lot of work, and this is just one of the papers, and I'm not going to be able to tell you everything in the paper. The paper is very long, but what we do is, as you can see, lots of inequalities, just inequalities after inequalities after inequalities. And what we do is we prove them. This is just an introduction, mind you. There are more sections in the paper. And what we do is prove them using linear algebra. And I'll say a little bit about technology in the proof, but mostly I'll still gonna talk about the inequalities and tell you what's going on. So let P be a finite poset. Poset means a finite set with an order relation, and we're going to fix an element Z, and I'm going to consider linear extensions. Linear extension is an order preserving bijection to numbers from 1 up to n. Okay, that's a linear extension, and by E of P I denote the set of linear extensions, and the EK is the set of linear extensions which which take value k on my element Z. Okay, and n of k is the number of such linear extensions. I know that was a lot of definitions. They're not going anywhere. I'm just gonna state the theorem and then give an example. So what we're saying is that the log-concavity for the number of such numbers n. Okay, so let's recap. What is the input? The input is a poset. Poset element Z and an integer k, and we're saying that number of order preserving bijections which take value k on element Z is actually log-concave.
Sorry, Igor, another stupid question. Is it true that it doesn't depend on Z, or you just don't include it in your notation?
Oh, it totally depends on Z. It depends on everything.
Okay.
Yeah. So I just gonna run out of space if I include all the P and Z and everything. Okay. So let's try some examples so you can see how everything works. And I'm doing slightly non-traditional way of drawing a poset, but I think it's more natural. So I'm going to have 3 elements, and the ones on the top are smaller than the ones on the bottom. Okay, and here are all the total of 5. So in this case, size of E is 5. There are 5 linear extensions, and they're basically you put 1 and 2 somewhere on the top, 3 and 4 somewhere on the bottom, and there's a tricky one when you put 1 and 3 here and 4 and 2. That's because you don't have all the relations between top and bottom. Okay, that's 5 linear extensions, and then you do a calculation. So where is my Z? Let me see. My Z is over there. So there are, what are the values? There are 2 4s. There are 2 3s, and there is 1 2. Okay, and those are my numbers. My numbers are n of 2 is equal to 1. There's only 1 linear extension which takes 2 on Z, 2 linear extensions with value 3, and the 2 linear extensions with value 4.
So if you interchange, for example, B and Z, then these numbers n will be different, right?
I don't know what interchange. If I make element B to be my fixed element, those numbers are going to be a little.
Yeah. Bit. Yes. I mean.
Yeah. The numbers depend on poset K. Element Z. They depend on all of this.
Mm-hmm. Okay. Thanks.
And obviously that's a log-concave sequence. 2 square is greater or equal to 2 times 1. Let me just try. So the question is, how do you prove that? And that looks really easy, actually. until you start thinking about it, and then you realize you don't know how to do it at all. And in fact, this was an open problem for a bit until Stanley sort of miraculously figured out how to prove it. Is the statement clear? Yeah. Very simple looking inequality for the number of linear extensions. And so in fact, this is so easy looking. I can tell you the whole proof, but let me not to. So what I want to do is I want to say, oh, there is actually a generalization of that inequality. We can have functions. We can have functions on linear extensions defined as a product of weight, and we can actually generalize inequality by taking sum over the weights, and that's what we proved. We proved the new result. We proved that those weighted numbers are log-concave. Okay, so Stanley uniform weights as general weights look very similar. Okay, so the weights themselves are not super important. The point is, for linear extension, you define as a you define for each linear extension a product of some weights. But the way we can prove this result is by using a new technology. That's sort of the point. Somehow, weighted version, unweighted version was proved by Stanley. Weighted version required a new technology, the technology of combinatorial atlas. That's just to make sure you get it before you all fall asleep. Okay. So new tools require new work, and let me give a big fancy example of that. The example, this is Brouwer orders. So what you do is you consider partial ordering on permutations. Let me sorry, partial order. So for every permutation, for every permutation sigma, you define a partial order by sort of thinking that everything is increasing down and to the right. So that element is smaller than this element, which is smaller than that element, but those two are incomparable.
So is this in some sense related to what Jordan was saying about it should be about automorphisms of the underlying objects? I mean, this is somehow capturing that. No,
okay. That's a different story. So it's just an example. So I'm defining the poset, and for this particular poset, linear extensions happen to be nice. They're lower order ideals of the Brouwer order. This is just me saying that it has to do with the rest of mathematics is also there. It's not that I'm saying something that's just combinatorics, as people say. And now in that case, and the numbers n of k is as a number of certain permutations which are smaller than a given permutation in the Brouwer order. And and still fixing a value of some on some element k, the value k. And now Stanley's inequality says something really unusual about the sizes of lower ideals in the weak Brouwer order. That is not something that follows immediately from any algebra at all. So we get this inequality as a really simple special case of Stanley. That's just me saying how general that is. And in that particular case, you can actually, let me speed up a little, and you can do the weight, and you can get a weighted Stanley inequality in this case to be the sum over all permutations of some weights. Okay, permutations are going to be elements, and they're going to have weights. Permutations smaller than a given permutation in the Brouwer order, and now we get a weighted analog of Stanley inequality, which is extremely mysterious even for the Breuer orders. I know that was a lot. So the point is I'm bragging how powerful I am. Okay, we can just move on. So now let's get to the proof, and I'm just going to show the proof without showing details. What I'm going to show is not actually from the original paper by Stanley. This is the original paper by Stanley, but I'm going to show you his own sketch in his own survey, where he discusses how to prove his inequality. And the way to do it is to define Minkowski sum of polytopes. So he was looking at Minkowski sum of polytopes. He defines mixed volume, and then he says, look, there is a famous inequality called Alexandrov Fenchel inequality, which says that for every two convex bodies, a sequence of these mixed volumes is log-concave. Okay, this on the surface, this has nothing to do with posets. That's just a general geometric fact. Now, then what he does is the following. This is for everything is from that's the whole sketch from the survey he wrote a few years later. So he's saying, look, I know it's a small fonts and it's intentional so that you cannot see. So here is what he's saying. I'm going to define completely explicitly a certain for every poset a certain polytope, and another polytope where one of the inequalities substituted by another one. And then a miracle happens. Those numbers over there turns out to become exactly those numbers n that you've seen on the previous slides. And you get the log-concavity for free. So that's what he's saying. You're saying that the numbers n, I wanted to keep the notation, are capital N, are up to scaling, are exactly the mixed volumes. If I didn't know that this was an open problem for years, I would have considered this to be not so interesting. So you try some other polytopes, you get some other inequality. But so what's amazing is he figured out what are the right polytope to obtain the inequality that people wanted to see. Okay, that's what Stanley did. I know you cannot see the details, and Stanley didn't write all the details, but that's the idea. Can I move on? So what are these Alexandrov Fenchel inequalities? The way to here is a somewhat more general version of that. So what we do is we define mixed volumes as a coefficient in the sum of so you think of a volume of look at the volume of a linear combination of polytopes where this sum is a Minkowski sum. We take a Minkowski sum of polytopes with coefficients, and the volume of that sum turns out to be a polynomial. And now we're looking at the coefficient of that polynomial, which corresponds to the product of all lambdas. That's how we define mixed volume. And then Alexandrov Fenchel inequalities are saying that square of one mixed volume is greater or equal to product of two other mixed volumes, and that, where it's really important to see that we have here the first two bodies are repeated, and in the second term the second two bodies are repeated. Okay. So so in a special case, when your polytopes are arranged first k equal then n minus k equal, you get a log-concavity because you have either an extra q or an extra p. And once this is done, essentially, once you know the Alexandrov Fenchel, this is sort of a headline from the past. 2 proofs in 1 year is as far as the headlines go in mathematics. You can realize that Alexandrov Fenchel is super powerful. And from my conversations with Stanley, that's actually how he found from the paper by Igor Pak, which solves the van der Waals conjecture. That's how Stanley realized that Alexandrov Fenchel inequality is important. What this is saying is that this formula gives a connection between a difficult function, which is a permanent, and the Minkowski sum, and that corresponds to just in case you have a whole bunch of axes aligned the boxes. So once you have that, you substitute it. You substitute it into this formula, and it gives you a really remarkable inequality for the permanent. And once you have that, the rest of the proof is relatively easy. This is basically, I don't know if you know van der Waals conjecture. It's not super important, but it's saying that of all bistochastic matrices, the permanent is the smallest at a uniform matrix. So what I'm saying is Alexandrov Fenchel inequality is remarkable. It's really powerful and for many years underrated. Can I move on? Yeah. So what Stanley did is really understood that it implies the Stanley equality, which used to be conjecture. Now I want to mention another measure. How do we know if we understood the inequality? And one way we know is if we understood the equality condition. So in full generality, the equality conditions for Alexandrov Fenchel inequality is a well-known open problem. In contrast with either perimetric inequality, Minkowski inequality, for Alexandrov Fenchel inequality, we just don't know for which polytopes the inequality becomes inequality. So for convex polytop, which is a special case of convex bodies, this was resolved very recently in a rather long paper by Schanfeld and Van Hendel. This is the date of the preprint. It's not published yet even. In the case of other polytopes, that was one of their main applications. Here is what they did. They showed that. Let's just concentrate on these two conditions. So they showed that you have an equality here, if and only if all three numbers are actually the same. And but of course, the proof is not direct. So first they showed that A implies C, and then C implies B, where C is an explicit way of saying for what posets. Remember, we have a poset P, and we have an element Z somewhere, and we have a number K. We have a number K which should go into linear extensions on that element Z. So they gave very explicit if and only if conditions when the inequality becomes an equality. And that requires extensions of Alexandrov Fenchel technology, and that's a rather long story, 82 pages, 4 figures, the usual. This is not something. I think it's to appear in ACTA. This is not something that you can just do on the fly. Is the claim clear? So one can argue now that we understand the Stanley inequality a little better, and what we can do. Remember, we found a weighted version, and that is something that Schanfeld and Van Hendel cannot do. So we can actually show the analog of their equality condition for the weights. We can show that for all weights. Remember, there were complicated weights. Now I'm saying that our proof is better than that proof. It can give more. In particular, it can give equality condition for the weighted version. So, this is Schanfeld Van Hendel result. This is our result, and our result is stronger. and there are no polytopes involved whatsoever.
Igor, may I ask you a provocative question?
Go ahead.
Will you submit it to ACTA?
Will I?
Yep.
No. Well, maybe, but not today. So what we do is, so as I said before, we prove a result using this is just one of our results. We prove everything using linear algebra, and while they use a sort of geometric technology, and our result, our generalization just pops out straight from our technology, while they have to develop technology to extend Alexandrov Fenchel. And somehow we get similar results A and B here and there. So we just have an extra parameter here because sometimes that's a global parameter. Sometimes you basically get more equality conditions. Can I move on? I want to tell you more. So how exactly can one possibly prove Alexandrov Fenchel inequality? That's such an important problem. There've been a lot of papers. So those there are original two proofs actually by Alexandrov. Wait, where am I? And then there are algebraic proofs by Khovansky and Tessier, and then there are more analytic proofs, and finally there is a Schenfer and Van Hendel. So there's just a variety of proofs, and our proof. So we don't actually prove Alexandrov Fenchel inequality because we want to deal with a special case of those polytopes. And so it's very natural to ask if there is an elementary proof of Stanley's inequalities. And the answer is yes. And that's also Schenfer and Van Hendel, but that's a different paper. That's a completely different paper where they proved it. Not the long one, not the ACTA one. This is proceedings of AMS. And so somehow they wanted to extract equality condition from their proof, their elementary proof of Alexandrov Fenchel. Same people, two different papers. However, they basically admit that there is nothing new. So somehow this elementary approach to Alexandrov Fenchel is way too elementary to give equality condition, and so they had to do something completely different and write a really long paper, 82-page paper, getting equality conditions for polytop, and we do something completely different. Everyone clear about the story? The story is complicated. However, the curious thing that our paper is actually motivated by that paper. This is our starting point, but we take it in a completely different direction. So from this point on, we're kind of reverse engineer and obtain linear algebra. So I wanted to mention, so how do we even start with trying to understand an elementary proof? And the way you start is, rather than me putting it in my own words, you basically say, look, log-concavity is saying that the determinant of this matrix, so determinant of this matrix is at most 0. That's what log-concavity means. But if you read the rest of the paragraph in the interview, you find out that there are Hodge-Riemann relation, algebraic geometry, blah blah blah, complicated stuff. So that's how Karim views this. Karim just seamlessly goes from matrices to let's call it algebra. That's not what we do. So we start with matrix has non-positive determinant, and we do linear algebra from that point on until the rest. We say that if you take a symmetric real matrix, it's hyperbolic if and only if we have a linear algebra condition. So which is basically something about quadratic form, and it's not super important what it says. It's a little more natural to think of it. It has at most one positive eigenvalue. Okay, so a matrix has one positive eigenvalue and everything else negative. Okay, that's a very simple condition, except that eigenvalue condition is actually rather unpleasant, while this condition is the one that's related to log-concavity. You can see so basically we obtain log-concavity by clever substitution of vectors into some matrix. So everything boils down to proving that some matrix is hyperbolic. Giant matrix, I should say, not a small one. So the way to think about it, number of rows and columns is the number of linear extensions. That's a large matrix. And that's what I just said. And now I can tell you in the remaining relatively little time, I'm going to make a really small font explanation of what's going on. I'm going to define a giant graph, absolutely giant graph with a whole bunch of vectors, and yeah, and I'm going to have essentially. Let me just say what this means. So we have a giant graph, and I'm going to prove a certain condition. So basically, I'm going to say that. So remember, we talked about this before. It is easier to prove a result by induction if you make the claim stronger. That's what sort of is happening here. We're going to prove that we're going to build a giant matrix, and we're going to build it from the bottom, and in this giant graph, and we're going to prove hyperbolicity condition for the matrices on the bottom by calculation, and then we're going to prove the induction. That's actually inductive step, that as you go up, the property of being hyperbolic remains the same. So one can deduce hyperbolicity for the vertices on. So think about it that way. So we want the matrix M, and you sort of go down. So base of induction is a lot of simple matrices for which you can do calculation, and then you prove by induction that the matrix M, the one that you want, is hyperbolic by using this something what we call local to global principle. And I know this is getting technical, but here is the way to define the graph. This is just to overwhelm your senses. This is not meant to be read. So what we're saying is, look, here is a giant graph on the right, and here are the matrices, and here is an explicit maps between the matrices. And once everything works out, you can prove everything by induction. That's what this slide says. And I'm just going to flip through that. I'm not going to even ask if you understand it, because obviously you don't. So this is not meant to be rhetoric. So here is what we actually do. We prove on the bottom with elementary inequality, on the top Stanley's inequality. However, the graph, if you look carefully, the matrix has parameters t and 1 minus t. And that is, those parameters are the bane of my existence. So it's very unfortunate that we have them, but we need them. So Stanley case corresponds to the case when t is equal to 0, but we cannot do the t equal to 0 case because the induction doesn't work. Because things collapse and you get extra eigenvalues which are 0. In order to get rid of them, you need to take this deformation. And this is also what happens when you prove Alexandrov Fenchel inequality. In the Champion van Hendel's proof, the ones that they have in proceedings of AMS, they also have an induction for the Alexandrov Fenchel inequality. They also have an induction, but then they take limit. They need to take non-trivial limits of polytopes because otherwise induction doesn't work. So somehow from convex analysis point of view, that's very easy. It doesn't matter. Inequalities are continuous. You take the limit and you prove the inequality for a dense subset of convex bodies, and then you take the limit and you prove them for all bodies. In combinatorics, that's very much unhelpful. And this parameter T is really the reason why Stanley inequality is substantially harder. I'm going to say about Mason's inequality in right after. So essentially, we at the end of the day, we do prove Stanley inequality and deformation of Stanley inequality just by pure linear algebra. Our proof, I would say, our proof is harder than Stanley's proof by miles. He just says, well, let's plug in Alexandrov Fenchel inequality, get the result. It does not give you extensions that we want for the deformation. It does not give a quality condition because Fenchel and Van Hendel had to work really, really hard to get them. What we do is we make a very hard linear algebra proof, but it spits out everything that we want. However, the whole reason I started the whole project is because I wanted at the end of the day to obtain an injective proof of Stanley's theorem. But it doesn't work because of the limit. We just have to take one limit when t goes to 0. Without that limit, the linear algebra proof doesn't work. And with this limit, combinatorics doesn't work. So I cannot obtain an injective proof in this way, and that's extremely unfortunate. But it is what it is. So in the remaining little time, I want to talk about matroids. Is everyone okay with me talking about matroids? This is going to be the last part of the talk. So I'm just going to assume that you've seen matroids before, and if you haven't, I think this example will have. We just think of matroid as a subset of vectors in some vector space. Could be finite field, the complex field, doesn't matter. And I'm going to denote by I. I'm going to denote by I collection of linear independent subsets. So we have a large ground set of vectors, and we take linear independent subsets. That's literally what was the motivation for Haster-Whitney when he defined them in 1933. And what he did is he formalized the two axioms for which these collections of subsets of vectors satisfy, and they're being closed down, and the exchange axiom, the one that we usually teach in linear algebra class, the one that defines the dimension of the vector space properly. Another example is a graphical matroid, and here independent sets are collections of forests, the same forest we've seen before. And they happen to satisfy the same condition. And in fact, all graphical matroids are linear matroids, but that's not super important at this point. So what I'm saying is, if you, collections of forests also of spanning forests are also form a matroid. Okay, those are independent set of matroids. Are we good? Can I move on? Okay. So now that we have matroids defined, let me now let me say this Welsh-Mason conjecture, which says that numbers of independent sets are log-concave. That's a remarkably simple inequality, which was open, as I said, for decades. And that it generalizes the claims that I said for spanning forests to general matroids. Okay, and that's adiprasita hookah. Everyone clear what I said? So whether it's a graph or a collection of vectors, there is always log-concavity for the number of independent sets. And as soon as a remarkable result like that comes out, people started proving more results, which are also conjectured. Happens. This is weak Mason conjecture, strong Mason conjecture, and you can see all the names of the people now with Anari and all. So what they did is they basically improved the log-concavity by a tiny factor. but those factors are important. Okay, they correspond to log concavity of the probabilistic version. When you take instead of I of k, you look at I of k as you think of probability probabilistic version. What is the probability a given subset is independent? Well, you need to divide by the binomial coefficient. So essentially, the theorem 1.3 proves log concavity for probabilistic version. Okay, that's what it does, and that's a short history of very recent development that happened. Are you with me? Yeah, because I'm starting to go real fast. So what we did is we improved it even further in a direction that was not foreseen or expected by previous people. So we defined the set of continuous. So for every independent subset, we define quant S to be the set of continuation. How many ways you can extend the independent subset so that it still remains independent, and turns out that there is equivalence relation on elements that you can define that way. So two elements are in the same parallel class if so fixing S, if S plus X plus Y is not in the independent set. So it's very important that it's not. And so then we define number of parallel classes for every independent set. We can define number of parallel classes, and so we have a new parameter P of k is the maximum number of parallel classes of independent sets of size k. Okay, so the way to think about it, we have a matroid, we have a number k, we have a parameter P of k. Okay, and straight from definition, that's at most n minus k. And what we proved in our paper with Chung is that one can replace. It used to be 1 over n minus k. So one can replace this number over there with that number. Oh, sorry, that's way. One can replace 1 over n minus k with this number. And the reason we could do it is the same reason as everything. We proved the result using linear algebra. So let me give you an example. What happens with a graphical matroid. Now you're in familiar territory. And this is just to emphasize that the notation now is I of n for number of independent set, but that's really number of n forests, spanning forest with this capital N edges, and you can see that our inequality is by constant factor better than the strongest thing that was proved before in this case. So we have a constant 3 over 2, while they have essentially constant 1. So in some cases, we get a substantial improvement in the ratio in log concavity, and it's all. And as I said, is this clear? Yeah, I'm getting close to the end. And in fact, this inequality is sharp for a cycle, and the only reason this can be proved is by using linear algebra, which with our giant technology of giant graphs and giant matrices, which is combinatorial and uses elementary linear algebra. It doesn't use any fancy of anything at all. And another way to see why we could prove what we prove is by proving equality conditions. So in fact, right in the middle of our project, equality condition for matroids we have figured out. So this condition is basically saying that all subsets are independent subsets, all small subsets are independent sets. That's what this condition is saying. Then you get inequality. This is if and only if condition. And we have something similar. We basically say, look, you get an equality for our refined version. You get an equality when all when the size of number of parallel classes is always the same P of k minus 1. And that's part of our work, and that's it. That's the end of my talk. Thank you so much. I'm done.
Thank you. Any questions or comments?
Is there a way to see any of this Hodge theory, you know, the role that it plays? Is there some, is it a fundamentally different proof?
Yes.
So there's no way to sort of track some of those algebra geometric ideas or differential.
When I say yes, this may be part of the ignorance. So I understand fairly well the Lorentz polynomial proofs. Jonathan Lee, who is here, can tell you more about some of that stuff. Essentially, you know, Hodge inequalities are a very big tool, and in fact, you can they can be used to prove Alexandrov Fenchel inequality. That's what Khovansky did. Khovansky TC proves Alexandrov Fenchel inequality using Hodge inequality. So our approach is it's sort of non-commutative. So in a sense, the kind of stuff that we can do for linear extensions, for example, is impossible to do with Hodge inequality at all, because commutativity is fundamental when you're dealing with Lorentz polynomials or that kind of algebraic geometry. And we can do it because combinatorics really doesn't care. We just look at some words which can be extended in a certain way. So so it might be that everything in the simplest case, when we don't want these objects become similar, but because we have those matrices boiled down to Earth, we can generalize it in a different direction, in the direction that algebraic geometry cannot foresee, or even Lorentz polynomials, which is a basic object, but they use derivatives. The derivatives are commutative. So essentially, so part of the reason why I didn't want even to start with matroid, I wanted to start with linear extensions, is because all that stuff that I can that we can prove for a number of linear extensions. Let me see where all the stuff that we can prove that for linear extension is just out of bounds for anything that Adiprasita Hukats and subsequent papers can do. That's just a completely different thing. So I'm not sure how convincing is that answer, but that's how I understand it.
Thanks.
Yeah, sorry it got technical at the end, but that's what I was told to do.
I think it's okay, but I have another question. So when you have those equality conditions that you solve, does the previous result follow from it?
The inequality?
Yeah, the equality.
I mean, it's
the last slide, I think.
You know, we essentially we first prove inequality, and once the inequality is proved, you can prove it. Once the inequality is proved, we just look, oh gee, our proof is actually better than that. We can do more. It's part of the same proof, essentially. Both inequality and equality conditions are two sides of the same, two coins of the same proof. So what we do is we set up the giant graph, and let's say look, we use induction to show that the matrix on top is hyperbolic. Where can we possibly lose and where the inequality can be strict? There are certain local conditions that you need to deal with. And then you check that throughout, in order for all local conditions to be equalities, everything has to boil down to a lot of equalities on the bottom graph. And that's really what's going on. So it's not like these are two different proofs, it's just one proof.
Okay.
But the proof is, so there is a reason why our paper is long. The proof is complicated.
I see.
It's elementary, but complicated.
Well, then it's not elementary. But what I was about to ask, if you can show me the last slide. Not the last, but the penultimate with the theorem.
This one?
86, I think. Yeah, this one. So does theorem, well, where is theorem 1.9? I don't know, but does theorem 1.10 imply theorem 1.8 in some shape or form?
Oh yes, totally.
Oh, it does. Okay.
No, that's actually quite easy. Mm-hmm. It's not. I mean, yes, it does. Because so the reason why I skipped 9 is because here I have both deformation and extension to parallel classes. I have two generalization in one jump.
Yeah, I see.
Yeah, and
but I mean, what I was interested in is then, sometimes you can have a stronger inequality, but when you turn it into an equality, it's a different equality, basically.
Yeah, so that's that's actually quite typical. So, for example, it's inequality. Some inequalities like G lambda mu nu greater or equal to 0 are very difficult, and equality conditions are very difficult. But G lambda mu nu greater or equals than -1, the inequality is the equality conditions in that case are very easy. This never happens. So so as you prove stronger results, equality conditions become harder because you're approaching the place where things become more difficult. So I hear your point, and that happens. And it's also it happens sometimes that you can actually understand equality conditions in polynomial time, but inequality is actually not in Sharpe even. This is so equality conditions can be much easier to prove. Mm-hmm. It's just that in those cases they were historically more difficult to prove, and what we do is just figure out one giant proof which proves it all.
Okay. And do you expect some other new results to come from this approach? Because I think what you say is basically somehow you have a general method, like this kind of a Hodge theory could be considered a general method, or the Alexandrov-Fenchel inequality can be considered a general method. Then your combinatorial atlas, would you call it also some kind of a general approach?
So it's a very general approach. Whether other people will figure out more stuff, I don't know. We're planning to write at least one more paper with more consequences of our approach. That's something in the works, and that's as far as I can tell. I think it's fair to say that there's not going to be that many people who are going to read our paper. It's a long and technical paper. So the stakes have to be very high. There has to be very important inequality for them to get through our long paper, and in order to prove that fancy new results that they want. We'll see if that happens.
Okay.
Are there any famous unimodality or log-concavity conjectures in combinatorics left after this work?
Oh yeah. Yes, there are. Lots of them. I'm not sure I'm prepared to answer what are they, but I can mention a cross-product conjecture, which I like very much. And if you go to my website, look for cross-product conjecture, it's a title in one of the papers. We proved the special case with Swihong and Greta Panova. But that's just one example of many open problems. But you know, with unimodality and log-concavity, lots of questions actually are false. So before proving it, I would actually suggest that you check them on a computer far enough first. And I'm still surprised that I think it's amazing that these conjectures are true. I'm old enough, and I remember thinking about some of this stuff like 20 years ago and concluding that not only there is no way to prove it, it's probably false. We just don't know, made sure it's horrible enough to disprove them. So yeah, I was wrong. The intuition is difficult to understand what's true and what's not, but some conjectures that are still outstanding might be false.
Mm-hmm. But if some of them are true, do you expect your combinatorial atlas method to prove some of them at least?
Well, we're working on it. We'll see.
Okay, gotcha. I mean, you just said that your paper is long enough for people to demand some kind of a, you know, of an illustrious result to read it. So hopefully you give them.
So what I can tell you what we did. What we did is we posted the follow-up paper, which is a special case. In the follow-up paper, we just prove we prove basically 3 short results, and one of them the theorem 1.1 straight from linear algebra, and the completely readable short proof. So it is often a balance. Should you write the most general result on long technical paper, or a short version of an old result which is not going to be as fancy? So we did both. So hopefully those who are interested in the method can just read the 20 pages that we have on the archive, which prove theory 1.1 just from scratch.
Mm-hmm.
And explains the way our technology works.
Okay. Any other questions or comments? Right, if there are no questions, no comments, let's thank the speaker again.
Thank you so much.
Thank you.
Thank you very much.
Thanks for the beautiful lectures.
Thank you.